Recording. Hello, welcome. Get excited for thermo. Oh boy. So what we're going to be going through is we're going to be going through the first test that I wrote when I was taking this course back in 2022. This is available on the course resource folder, and I posted it in the chat where this recording will be posted as well. I can't guarantee its similarity to what you folks will be writing because we had a different prof at the time, right? We had Dr. Kish, now you have Dr. Foriapoku, so I can't guarantee the similarities, but it should be similar topics. If there's anything that isn't covered in this test that y'all have gone over and you're like, what the hell is this? I'd be more than happy to help. Thermo is really applicable in all your upper year courses, so like literally phase transformations is just 2D. That's all we've done so far. Like 90% of our course content is just being 2D all over again. So I love thermo. As a bit of a warning, I guess. So I know how y'all have 2 midterms next week. I also have 3 midterms next week. So have I prepared for this? No. That being said, a lot of this content is still transferable, so I believe in myself to explain it. But I'm not gonna come up here and be like, yeah, I know everything about thermo. I prepped so hard for the session. Like, no, literally, I grabbed my notes this morning and I downloaded this document about 5 minutes ago. So that's kind of where we're going with. Any questions before we get started? Slay. Okay, we're gonna minimize the online version, but you are unmuted, so if you have any questions, like just yell. Okay, so I believe this test was meant to be for 50 minutes. I think we were given 2 hours, because it was our first in-person midterm ever. So was it our first in-person test ever? Maybe. I think so. Anyways, I don't know how long like it actually took me, but the point is, however long it takes us, it shouldn't be too bad. It starts off with some definitions. This was very classic of our thermo tests back in second year, was they always started with some sort of definition. So we're going to start, the first one, I guess, 1I is defining the activity of component I in a mixture. So there is a formal definition for activity, and then we can get into what does it actually mean. So activity of I is defined as the fugacity of component I all over the fugacity of component I in the standard state. So I'm going to write that out in words. So that's fugacity of I in the mixture all over the fugacity of I in standard state. Also, before I forget to mention it, I mentioned it to folks here in the room, but there are like the actual like formal solutions that are posted on they were posted on Avenue for us. They're in the course users folder as well. I'm going off of what I wrote on this test because that makes most sense for me, and it kind of shows you what you actually need to say to get marks. So basically, this is the formal definition of activity. What is fugacity though? I don't know if that was another one of the questions. It was not, but fugacity, if we want to just kind of get into a bit more detail, the definition of fugacity, basically Fi over Pi goes to 1 as Pi goes to 0. So basically, as you get more closer and closer to ideal, like as you have a low pressure for gases, you get closer and closer to ideal, then your fugacity approaches that pressure, where P is the partial pressure. Partial pressure of I in a gas mixture. So that's kind of what fugacity is, but if we go back to activity, we can start to talk about it a bit more into what does it actually mean as opposed to just this ratio of fugacities. So if we have, it's a bit easier to talk about when we deal with ideal solutions, right? So let's look at an ideal case. Remember, this is like, for example, at low pressures. What we just talked about for fugacity is that the fugacity is going to be equal to the partial pressure of that constituent. So we can rewrite the activity as the ratio of the partial pressures. And this is a bit easier to kind of visualize because you're like, okay, it's the partial pressure of this component I in the mixture versus when it's in standard state. And standard state is a bit, at least for me, easier to visualize when we're talking about gases and pressures because I know what a pressure is. What is fugacity? It's really hard to actually figure that out. So that's just kind of a little bit more of a like intuitive understanding. If we're dealing with a condensed phase, so it's not just fully gases, then instead of pressure, like so for condensed phase. So for condensed phase basically means like solid or liquid. We don't have necessarily a pressure, but we have the partial vapor pressure. Pi is going to be equal to the partial vapor pressure. And that's just like, this is like kind of a side note here, is that the partial vapor pressure, let's say we have a liquid. Ooh, this is a liquid. And then even if it's like quote unquote all in liquid form, there's still going to be some sort of equilibrium going on between the liquid form and the gaseous form. So we're going to have a little bit of gas, no matter what. So this is just like, oh, we have a little bit of gas, and this gives the partial vapor pressure. So then if you want to actually put this all into words, which I'm just going to say instead of writing down in the sake of time, is that what I wrote down is activity is a ratio between the components, either like Fi or Pi, on the same value at standard state. So it provides an indication for how far the substance is from its standard state. So basically, to rephrase that, maybe in less wordy, Sarah's stressed out and writing a test kind of vibes, is that if activity is close to 1, that means the pressure, like we'll just say we're dealing with ideal, right? The pressure is roughly equal to the pressure in the standard state. So we're pretty close to standard state. If the activity is not close to 1, that means that the pressure is not close to the pressure at the standard state. So we're not at standard state. And that's kind of how you actually interpret these activity values. Alrighty, does that make sense? Slay. I swear to God, like every single lecture, we'd walk in and Dr. Kish would be like, "Okay, friends, what's activity?
Yeah.
Define me activity." Does Dr. Nana?
Class.
I don't actually think I've ever answered that question because it stressed me out too much.
He asked me questions in lecture that like in my head, I might know the answer, but to put English into it,
Yeah,
I couldn't tell you.
yeah,
You know,
such a mood. Kish was really big on asking us all these questions, then nobody would answer him, and then he'd always like ask me and
2D thing.
maybe. Anyways, the next thing that it asked us for is the definition of the chemical potential. So again, we have a mathematical definition of chemical potential, and it's given by a literal mu, chemical potential of component I in a mixture, and this is just going to be equal to the partial differential of like the Gibbs energy, dg over dni at p, t, and j, and k, ... So what does this mathematical gibberish mean? This is the sign for chemical potential. I'm glad you know that, Bryson. And this is basically saying this is the change in Gibbs energy as you change the amount of substance I while keeping everything else constant. What did you say?
I did so many subscripts. It's crazy.
Yeah. Well, basically, like, I mean, we have the pressure, we have the temperature, and then we have like, you can keep this going as many, like, because you can have it like not infinite, but you can have a lot of like substituents. So that's why like we represent them in like NJ, NK just to represent whatever else you have in the system.
It makes sense, but it just scares. Like,
yeah,
I don't know. It makes me nervous.
Yeah, that's fair.
I don't know.
Yeah, you won't actually have to like mathematically, do you? I don't think you ever have to actually calculate this. But when you get into upper years, then chemical potential is used, like, for example, instead of concentration, because that's what actually determines the behavior of a system. When we're like talking in second year courses, usually we just deal with concentration, but in reality, it's the chemical potential that matters. So that's kind of why this is important, because everything comes down to how the Gibbs free energy is changing with a substance. And then a fun fact about this that I wrote down, I seriously doubt you actually needed in your answer, is that if you had an infinitely large system, so for example, as you changed the amount of moles of substance I, it wouldn't actually like change the overall composition, right? It'd just be changing the amount of moles in the system. Then you would not change the molar fraction. So you wouldn't change Xi, no change there, but G would change, or G would increase by mu I. So that's kind of another way of thinking about it. Is like, this is the change in Gibbs free energy if we just add one more mole. I'm going to erase that because that actually makes no sense written down. Any questions about that? Soleil. The next one was standard state of component I. I actually lost half a mark on this question because I didn't know how to English. It was really upsetting. So standard state is defined as basically, the state at which the activity of a substance is equal to 1. So, for example, if we have a liquid or a solid, that would be pure. So pure liquid or pure solid. So in that case, xi would be equal to 1. Yeah, I think that's what's most important here. So that's just kind of a given, like when we say standard state, what does that mean?
Literally these first definitions,
still love all the
it's 10 minutes at every
definitions.
class.
Man, it's probably gonna be on your test then.
It's probably on the test, yeah, I'm just
Yeah.
thinking about.
I still can't tell the difference between standard state and reference state. Like,
Reference state is the state at which we're at, isn't it?
Yeah.
And then standard state is like when this is true.
okay, if you say it like that.
Yeah, no, but like when you're sitting there and they're like, what's reference state? You're like, I don't know. That would be me at least.
Every one word that you say, Dr. Corey says about 10.
Yeah.
And then
And I feel like that's like the same case with every single review session we do,
yeah.
with like every single prof.
Like it also comes down to the fact that I've done this course multiple times and I've like written the tests. So like I know what you actually need to know for this, where the profs are like, you need to know all the information. I'm like, well, what do you actually need to know? So yeah. Anyways, the next one it asks us is Henry's law. So Henry's law is nice little fun one. Whoa, Henry's law. And this kind of comes down to what we were talking about, I guess previously, kind of with activity and molar fractions. So let's imagine we have, oh God. We're gonna make a little graph here. I feel like, are any of y'all on 2Q right now?
Yeah.
Whenever I make things like this, I just it gives me Marek vibes, like Dr. Nyanskas, like you know when he like makes a little graph and he does all the air. Yeah. Anyways,
How are those tests?
I thought they were pretty fair.
No. The TA said as long as you write things down, he'll give you marks. It could be. He said it could be a different language. He'll give you marks. like he's like, if you don't tell the prof, then we're good. Yeah. Not even.
No, we have a recording.
Oh,
Just
oh,
kidding.
scrap that. Scrap that. Scrap that.
Um,
I know you're right.
I actually quite enjoyed 2Q personally. Anyways, Henry's law. Basically, we have the system, right? And we want to plot how does the partial pressure of component I. Anyways, as we vary like the amount of B in the system, how does the partial pressure of that change? So if we had an ideal case, it would go in a straight line. As you add more B, then you get more pressure of B. But in reality, that isn't always the way systems behave. So, we would have, like, I drew that little, supposed to be a straight line. What we're actually going to have in a case of Henry's laws, we're going to have something that looks a little like this, right? It's going to have a little deviation. I drew this as negative deviation. But what Henry's law states is that at low concentrations, then we're going to actually have, a linear approximation, right? So at low concentration, yeah, so this is going to be, yeah, so we're plotting P of B. So at low concentrations, then we have a linear deviation. And we can plot this intercept, right? We can figure out what this intercept is. I'll do that in a different color. We'll do it in red, why not? This intercept here is going to be equal to Ki. And what we can say, Henry's law, like mathematically, is that Pi is equal to Ki times Xi. So in this case, that would be Pb is equal to Kb times Xb, where Kb, remember, is that intercept. Xb is like the molar fraction. And then Pb is the partial pressure of B in the mixture. This applies, as mentioned, for low concentration, so like dilute solutions. And because this isn't following a straight path, then this is a non-ideal case. Any questions about Henry's law? Go for it. This? I just wrote int as in the intercept. Yeah. Yes. We can do that after we go through the test. Remind me. So many questions. Bryson.
And then, are you free 5:30 to 6:20 every Tuesday and Thursday to come to class?
Go to class.
Yeah, it's been summarized. Cause like I've been stuck in this contract, this has not made sense. Until it probably grow down.
Gaskell made sense.
Oh my god.
I read the textbook and I heard an audible gasp come out of my
Oh my
mouth
God.
because it clicked in my mind.
I will say, if y'all like advocate enough, I tried to TA this course this year and they didn't have any openings for undergrad students. But if y'all like yell at Dr. Zurab
What?
enough,
Okay,
No.
no. The TAs in this class are so bad,
Stop.
so bad.
okay, I'm gonna stop the recording. I'm gonna mute myself real quick. I'm so sorry for people online.
Was asking why you're muted, I told her.
Okay, wonderful. I am now unmuted. We're gonna get back to this. Okay, tangent done. Sorry for folks online. We were talking about things that did not need to be recorded. Alyssa, did you have a question? So if we have an ideal case, basically an ideal case is everything is nice and easy peasy lemon squeezy, right? We don't need to think too hard. So in an ideal case, it's just gonna be a straight line. It's gonna be constant the entire time, and that's defined as Raoult's law, right? Is that it's gonna be ideal. It's gonna be straight. Not that being straight is ideal, but in this case it is. So sorry, I had to. So in this case, basically, whenever we see any sort of deviation from that, we know that we have a non-ideal situation because it's not following that direct path. Does that make sense?
Yes.
Yes. Alrighty, are we good to move on to the next definition? Slay. Okay, the last definition we had was, oh my gosh, positive deviation. I think that's why I did negative deviation for that one. So positive deviation. Oh, this is actually one of the questions that y'all had. So basically, remember when we just drew that graph up there? Well, we're going to redraw it again, but very slightly different this time. So once again, we're going to have the partial pressure. We're going to have XB increasing. And then we're going to draw in black, we're just going to draw a nice little straight line here. So that line represents ideality. This is the ideal situation because it goes all the way from zero pressure to the pressure of B when it's the only component in the system, right? When we only have B, so I guess XB is equal to 1, it would be just direct correlation between the amount of atoms you have and the amount of pressure you have given by this thing, given by this component B. But in a non-ideal case, with positive deviation, it's going to be above that. It's going to be like something like that. And we would get like, you could, that's actually, I'm going to draw it slightly less steep, but it's going to have something like that. And we can get like the slope of the line there. So now let's kind of break this down into actual words instead of just drawing. So we have in black here, we have the ideal case, which follows Raoult's law, which says that Pi is equal to, or I guess P B. I'm actually like blanking on what the equation is because I'm like, it's not equal to X because there's like,
Is it?
yeah, you're so right. No, because like the pressure, like for example, if you were here,
Yeah, because the P naught is
okay, we got it.
equilibrium.
See, y'all understand this. So basically, this is just Raoult's law, right? Essentially, this is saying we go in a straight line from 0 to the pressure of B. I am unmuted, right? Just want to make sure. Yeah, the pressure of B when we are only B in the solution. Here, however, we have positive deviation. We know that it's positive deviation because it's above the ideal case. The pressure is greater than ideal. And then Henry's law, remember, I drew this here. This is just Henry's law as we stated before, is that it behaves linearly at very low in very dilute solutions, right? So at the very start, then it has a bit of a linear behavior here. This occurs, so positive deviation essentially means that we have the solution, right? So we can think of like, again, we have a liquid, right? And then we're measuring the gas up above. And we have A and we have B in the solution, right? So we can have A and A bonded together, we can have B and B bonded together, or we can have A and B bonded together, right? And what the system wants to do is it wants to minimize the total energy of the system, right? That's kind of the core concept behind all of thermos, that we want the minimum energy possible. So it's going to form a proportion of AA, BB, and AB bonds depending on what is lowest energy. With positive deviation, then we have AB bonds are much weaker. So essentially what that means is that when we mix this together, right, then it's going to be like, whoa, AB bonds are a lot less than just A or just B, right? So we're going to form a lot of those, and because we form a lot of those, it's going to like be ahead of where you would expect it to be in terms of like the pressure, however you want to think of it. But you can just think of it like there's more of those AB bonds, there's more interactions, and the way that they worded it in our lecture is that there's a greater escape tendency. So what that means, AB bonds are weaker, is that there's going to be a more tendency for it to leave the solution and become a gas. Did you actually need to say that? I don't know, but that's just a fun fact.
Talk about the bonds like a lot.
Yeah.
What ones are more like?
Yeah.
Isn't it if it's like if ABs are more like have that higher tendency, then we have the positive deviation, and then the other way is.
Yeah, so because AB bonds are weaker, that means we have more of a tendency to have the AB bonds. So more AB bonds will be formed. I think. We can also say in this case that delta H of mixing is greater than 0 because it's positive. Question.
When you say greater escape tendency, does that mean like AB bonds?
Just in general, the solution will have a greater escape
Like,
tendency.
like,
Yes, I
AB
think it'll
atoms?
typically just be the AB mixture. Don't quote me on that, but
And also. AB bonds?
well, we have the 3 cases, right? So like kind of an aside, we have ideal, positive, negative, right? So in an ideal case, I'm going to say E is equal to the bond energy because this is what we did in one of my courses last semester. In an ideal case, the energy AB, like the bond energy, is equal to the energy AA, which is equal to the energy BB, right? These are all the same. That's kind of, the system doesn't care if it's like that much of like how much it's mixed. It's just like whatever. It's all the same to us. Same bond energies, whatever. I believe that for positive deviation, please correct me if I'm wrong. For positive deviation, then EAB is smaller than EAA, EBB. It's like 1/2 EAA, like the average bond energy. And then for negative EAB, it's greater than 1/2 EAA plus EBB. So that's kind of how it has to do with that. If y'all remind me when we're done going through this, I can check my notes to make sure like I have those signs actually correct, but it has to do with how the bond energies relate. Does that make a bit of sense?
And is that just like a thing? Like that's just how it's supposed to be?
What do you mean?
Like the bond energies are supposed to be like smaller for AB?
Well, it depends on the
Positive
system.
deviation.
Yeah. Essentially what happens is like, um, it's not like they're smaller in AB because of the positive deviation. It's like the bonds are smaller in AB, so we get positive deviation.
And that's just like. Oh, like it's like weaker.
It depends on the system and like what the substituents A and B are. So like what are their charges? What are their crystal structures? What are their like what is the temperature? What are their like hydrophobicities and all that jazz?
Okay.
Yeah.
And the ideal case would be showing Raoult's law, and the positive and negative shows the Henry's law.
Yes.
So if we have like, so in the negative case, so if the energy like AB is greater than that of AA and BB, like we're not gonna have like them leave the system.
Yeah.
A negative enthalpy. And then that's a negative.
Yeah. The way
So that's like if it's negative deviation of a negative enthalpy.
Yeah.
That's a good way to.
the way I thought of it is like, oh, like if they really, really like each other, you know, they have really, really big bond energy, like, ooh, we like each other. We're gonna stay together. We're gonna stay in the system forever, right? We're really happy here. So that's why we're gonna have the negative deviation because they want to stay there. They're so happy. That's how I thought of it. So
No line could be like the house.
yeah, sure. And
Actually, I had that question too.
so enthalpy, right? When we're having a reaction, when we're mixing things, then the enthalpy, I think you get more into this in the second half of the course, but it's fun. We're going on this adventure now. Enthalpy has to do with like, you know, like delta H of like the like products minus delta H of the reactants, right? So what we're doing is basically we have to break all of the bond energies. We have to break all the bonds in AA, and we get to form AB. And delta H of these bonds, I believe, is actually negative. I mean, I could be completely tripping up here, but when it is really happy in the AB form, when it is really happy in the AB form, then what's going to happen is we're going to have, you know, EAB. It's really happy in AB. The energy is bigger than A or BB, right? So we're going to have, let's say, EAB minus 1/2 EAA plus EBB, right? And this is all negative, but like if we can just deal with like this being positive, for example, then if we know that this is bigger, magnitude-wise, then we're going to have a negative overall delta H, because remember, this is a negative value. So basically what's going to happen is it's going to form, and because it's more like there's stronger bonds, then you're going to release a lot more energy when you're forming those bonds. Because they're like really happy being formed. So it's going to release energy, and that's going to give a negative delta H value. Whereas if it's less happy to form those bonds, you need to put in energy overall. Like you're losing energy as you break those bonds and then form the new ones. It takes more energy to break the bonds than it does to actually form the new, than it releases by forming the new ones. So it doesn't like the new bonds. It isn't happy in the AB system, and you're going to have a positive delta H. Does that kind of make sense? It comes down to like the definition of what is delta H, right? It's just like the change in bond energies. You can think of it. Alrighty. Make kind of sense? Slay. Okie dokie. So that was some good old definitions. Now we're going to go into question 2. Question 2 caused a lot of people a lot of stress in our test. And this was the motivation for me making bucket hats that said keep calm and PV equals NRT. Like, I'm not joking, this was the question, because you're like, we didn't really do ideal gas law in this class, right? And then all of a sudden there was a test question that about ideal gases, and you're like, what the hell is going on?
I have no idea what they're gonna like actually like do.
PV equals NRT
There you
potentially.
go, potentially, yes.
Wait, Sarah, one more question to.
Go for it. Yeah.
So we know what happens at like the corners of
Yeah.
like that graph, like the,
Yeah.
when we have both the positive and negative. What the hell is happening in the middle?
It's just doing its thing. You don't have to know like theoretically what's going on. Just know that it eventually goes from, you know, the straight line of Henry's law, and then just like eventually makes its way back towards that positive.
So we don't need to.
Just know that it's non-ideal, so it's not behaving how we think it would.
Oh, okay, that's
Yeah.
it.
That's all you need to know. I mean, I don't know how to actually describe what's going on there. It's just like funky dunky interactions, you know? You know?
No, I'm like, 'cause
I have no idea what goes on in the middle.
okay,
So,
lovely. I just wanted to know,
yeah,
like something.
all good. Alrighty, so this question, well, we'll see how well I can follow my notes. Oh my God, I remember when I was calculating this, I forgot a 0 at one point, and I didn't realize till I was checking my answers, and I was like, oh my God. Anyways, I'm gonna start, whenever I have questions that are calculations, I start by just writing out everything that I know as I go through the question, and this helps me kind of get my bearings. It really helped me on this test because I was so confused with this question. So, as a bit of a standard, I'm going to represent argon by A. I'm going to represent magnesium by M, and I'm going to represent copper by C. So that's just going to be how I'm going to use subscripts throughout the rest of this question. So we know Na is equal to 4.113 moles. Inert just means that it's not going to react. And I know that Pa is equal to 1 atmosphere. I know that in the crucible, then we have XCu is equal to 0.22. TCu is equal to 740 degrees C. I'm immediately going to change this into Kelvin just in case. Is equal to 1013 Kelvin. And then I know that say this, the pressure of Cu is going to be equal to 0. I guess I'm just going to put this down here. And then X is equal to question mark P question mark. And we know that the change in mass as that argon is passed over top is equal to 38.2 times 10 to the negative 6 kilograms. I guess times 10 to the negative 3 grams, because that's probably how our calculations are going to go. We'll see. Or I'll just write out as milligrams and we'll convert it when we need to. So then it wants us to figure out what is the partial pressure of magnesium, then we want to find the activity, and then we want to talk about if it's an ideal solution or not. Other information we're given is that the molar mass of magnesium is equal to 24.305 grams per mole. And we know that R is equal to 0.0821 liter atmospheres. And then we're given this funky equation for log P mg. So I'm going to start by just doing something quick. I know that, well, I mean, if I kind of draw the situation, just to give you a bit of information as to what's happening, we have, a solution in here, graphite crucible, and we have some in here. I don't know, this is a bad drawing, but essentially in there we have, Cu plus Mg. And then we pass argon over top. And as we pass this argon over top, then basically some of the magnesium leaves the molten alloy and goes into the air. Mg. And we notice, and we know how much we're going to lose. We can figure out based off the change in mass of this. So that's what we're going to be dealing with. So I'm going to start by saying this is initial. So the first thing I'm going to be is like, okay, well, how much magnesium do we actually have at the start? So we know that we only have magnesium and copper in the molten alloy at the start, right? So we know that the sum of, the molar fractions in a component is equal to 1. So know that 1 is equal to xCu plus xm. I guess I just turned it to Cu and then m said mg, but I'm leaving it, I don't really care. Which is equal to 0.22 plus xm. We can get xm is equal to 0.78. I'm just going to put that in here because that might be helpful later. Is it actually going to be helpful? I could not tell you. Go for it.
Is the XCU, is that the crucible mole fraction or is it the copper mole fraction?
It's the mole fraction of copper in the crucible. Because the crucible is just the thing that's holding it, right?
Okay, yeah. So
All good, all good. The next thing I'm going to do, because I'm like a little lost, I'm like, I don't really know. I'm given this equation. I'm going to calculate that equation. Why not? It's kind of fun. So I know that log of P mg is equal to negative 7150 divided by T plus, 8.182. 8.182. And the temperature we're going to be using here is, has to be in Kelvin, right? We know that T is equal to 1013 K. So we just need to solve for the pressure here. We can say that P is equal to 10 to the power of negative 7150 all over 1013 K plus 8.182. If you were to calculate this, we get P mg is going to be equal to 0.0, or I guess you would, go away. You would get a value of 13.297 millimeters of mercury. Why is it millimeters of mercury, you ask? Because in the little subscript here, I'll do this in bright yellow, it says that it's giving it to us in the millimeters of mercury, so we have to take that into account. Well, that's kind of terrible quality, I just realized, I'm so sorry. Anyways, we have to take that into account, but we hate that unit. I hate millimeters of mercury. It's so frustrating to deal with. So I'm going to convert it. I know that 1 atmosphere, it's given to us in the question, is equal to 760 millimeters of mercury. So we can get that the pressure of mercury is equal to 0.017496 atmospheres. And now we need to ask ourselves, what actually is this pressure? What does this actually represent? And we can go back to the question, and it says that this is the saturated vapor pressure of the liquid magnesium. So essentially what this means, by saturation, that's as much as you can possibly get in the environment. So if we go back to that little graph we had, right? If we have PI and then we have like X, I guess, Mg, P, Mg, assuming ideal. It's not going to be ideal, but let's pretend it's ideal. Oh, go away, lines, I don't like you. It's going to be this value right here. This is the maximum we can get. This is going to be the saturated pressure. So we can add the little naught symbol we had, right? Like P, Mg, naught. This is what we just solved for, is that value there. So we know, we want to find the partial pressure, though. We don't want to find whatever we just found, right? Like, yeah, it's helpful, but we want to find the partial pressure. So we got to remember how we relate these two together. And what it comes down to is what you folks so clearly and eloquently told me earlier today, is that the pressure of, I guess we'll call this mg, I don't know what I'm saying, be here, the partial pressure of mg is equal to, what's that doing? We know that this is equal to the activity of mg times the pressure, like saturated pressure, times mg. Then we look at that and we're like, well, calculating the activity is the next step in the question. So we clearly can't take this approach. So we have to come up with a different way to solve for what this partial pressure is. And this is where I say, keep calm in PV equals nRT, right? Because PV equals nRT will give you whatever the pressure is in a given system, which will be the partial pressure. Go for it. We're not actually going to be using this equation. So I'm going to say this is, we don't have energy, AMG. I'll explain in a sec. AMG is unknown. Can't use this equation. Well, does AI always equal XI? This is only in an ideal case. Do we know if this is an ideal solution?
He did say to always assume ideal. He did? Yes.
Assume ideal gases. Do not assume ideal solutions. There's a difference. And we're going to see that difference in this question,
Well,
actually.
because in the third.
Mhm. So the gas itself can be ideal, right? It can follow PV equals nRT, right? But actually getting to that gas, right? Like evaporating out of our molten alloy, and that process of, forming the mixture, forming the solution won't necessarily be ideal. Does that distinguishing, what is the word I'm looking for? Distinction. Does that make sense? Beautiful. So we're going to say, does it ever actually say that it's an ideal solution? Well, we're going to say assume ideal gas, right? So we're just going to say PV is equal to nRT. So we know P total is equal to 1 atmosphere. Or I guess we know that the P saturated would be equal to some value that we just calculated, right? We know R. I'm going to draw smiling faces. We know T. Can we, and next we look at N. V is a little tricky. Oh, what do you mean my battery's full? You hacker. Give me a sec. Is there a plug nearby? That is a real question. Anybody see a plug? I'm just going to sit here and cry if my laptop dies. I feel like there should be plugs. Like, how do you not have plugs right here?
Wait, wires.
I know.
Living in the desk.
Plug reader, like.
Oh, yeah, there's one on
Yeah,
the
there's
floor.
one. Where's the phone?
Why is there one on the floor?
I know, it doesn't.
Where's it on the floor?
There's like 4 here.
Oh, this room is so whack.
Yeah. Where's that whole thing connected to
It
though?
goes inside the box and it just disappears.
What?
Like,
Is there a plug inside the box somewhere? There has to be.
not that I see. It's just,
So weird.
yeah.
That's so odd. Careful, it won't charge you. Okay.
Yeah. Oh, we're chilling.
It's an interactive session.
Yeah. Sorry, online friends. We had some difficulties finding a plug. Anyways, so we're like, okay, we don't know everything in this ideal gas equation, but let's see what other information maybe we were given that we haven't used yet. And the big thing that we were given is we were given delta M, right? We know that delta M is equal to, what was it, like 38.2 milligrams. And now we need to figure out what this delta M actually means. So if we go back to our little drawing above, right, we had copper and magnesium, and then we lost some mass somewhere. But it told us that the copper doesn't leave the solution. The copper is nice and happy there. So now this change in mass is equal to the amount of magnesium that was lost. So it was equal to the amount of magnesium that went into the air. So we can say that delta mass is equal to the mass of magnesium in the air. So we also know the molar mass of magnesium is equal to, what was it equal to? Like 24,305 grams per mole. So we can say that the number of moles is equal to the mass divided by the molar mass, like the molecular weight, which is equal to 38.2 times 10 to the minus 3 grams over 24.305 grams per mole. And you would get that a total of 1.5717 times 10 to the negative 3 mole of magnesium entered that gaseous phase. So now we have N. Yay. What we can try and find is we can find the actual volume that this all takes up. So we're going to say V is equal to N RT divided by P. And then we're going to use a saturated pressure here. Oh, I lied. We're not going to use a saturated pressure. Why did I say saturated pressure? We are going to deal with the entire system itself, right? So the system that we're dealing with, right? We have the argon gas that's passing over top, and that's just going to be a 1 atmosphere. Because we're dealing with the whole jazz. What am I doing? Oh my gosh. So we calculated NM, but we're like, wait, we're trying to find P, right? We're trying to find this. Sorry for me being all over the place. My notes are all over the place. We want to find PMG is equal to what? But before we can find that pressure, we need to calculate what the volume is that it's going into. So we're gonna look at what other information we have, right? So this is all for magnesium. But we know that we also are dealing with argon, right? We have some argon that's also going to behave ideally. PV is equal to nRT. What information do we know about argon? We know N, we know P, we know N, we know T, right? So we can take this and we can solve for the volume of that argon of AR. You kind of see why we're doing this? My explanation, no, you don't see it. Okay, my explanation was a little all over the place, which is why. So I'm just gonna, essentially, if we go back to our drawing, we're going back to our drawing. We want to find out the pressure of magnesium, right? So we're PV is equal to nRT, right? We're like, okay, we want to figure out what is this pressure when it's in the gas phase, because we know it's not really going to be equal to the saturated pressure, right? We know that's not going to be the case because it's not going to be a fully saturated solution because we're mixing with the argon. So we're like, we don't really know what that pressure is going to be. So we need to know what kind of volume it's being absorbed into. And what we're going to say is that as we add the magnesium atoms, like the magnesium molecules to the gas, because there's so few compared to the amount of moles of argon, we're not actually going to be changing the volume much, right? We just have like, you can imagine that we have like this room and then you chuck a little bit more air into it, right? Like it's not actually going to change the volume of this room. It's not really going to change the total pressure either, but we are going to be changing. So we can use this as like the base state for how much we have. So what we need to figure out is what is that volume that it's being, I guess you could think of it evaporated. What's that volume that it's being evaporated into? And for there, we can look at what gas is already present. Right? And that's where we have the argon. And we're using that argon to figure out how much space do we have for that magnesium to go into and calculate the pressure. Question. So I never actually wrote anything, but what we can kind of look at is we just calculated the number of moles. 1 times 10 to the minus 3. We have how many moles of argon? 4.113. That's a really, really tiny baby amount. So we can just say that the volume is going to be the same. Does that make sense?
Yeah.
Amazing. So we can take this and we're going to say 4.113 moles. We know that R is 0.0821 liter atmospheres. The trick here is to make sure you just watch your units, which is why I'm writing them all out, times 1013 Kelvin, all divided by 1 atmosphere. you would end up with a value of 342.067 liters. Yeah, so we're gonna get liters. So now we can take this and plug it back into PV is equal to nRT. So P is equal to nRT divided by volume, and this is going to be now for magnesium. So now we're just going to take those values that we just solved for. So we're going to have N is equal to 1.5717 times 10 to the negative 3 mole. R again is 0.0821 meter atmosphere. And then we know the temperature is still 1013 K. We divide this all by that 342.067 liters. If you do that, you get a value of 3.82 times 10 to the negative 4 atmospheres. And this represents the partial pressure of magnesium. So that's part A. Go us. I'm gonna wait till I stop seeing people like writing down and looking up and writing down and looking up before I move on. And this is the bulk of the question, is understanding how do we actually like do anything with this information we're given, what is happening in the situation. The next stuff is gets into like a little less calculations and a bit more of just like the application of like the concepts we were talking about earlier. Wait, what? Yeah. Like, I'm not joking. Like, people were like having like breakdowns because remember, this was also our first ever in-person midterm, right? It was like one of our first ever closed book midterms since we got to like, since you first year, closed book, online, So like this was like our first ever like closed book in-person midterm, and then like it's like something we haven't really talked about because it's PV equals nRT. And like Dr. Kish was walking around the room while people were like, I don't know what's going on. And I remember being like, I'm not gonna ask for help because I'm too stubborn, but I'm gonna like frantically listen to what he's telling other people. It was such a disaster. Anyways, question B asked us, I guess two. It wants us to find the activity of Mg in the molten alloy. So this is where we go back to what we were kind of talking about before when I was like, wait, we can't calculate the pressure this way because we don't have activity. And this is where we say that Pmg is equal to Amg times P standard, or P saturated Mg. So you can calculate A is equal to P over P saturated. We already calculated both these values, remember? 3.82 times 10 to the negative 4 divided by whatever we got above, which was 0.017496, which is equal to 0.0218. And there's no units for activity, so we just have a nice little answer. That's all we need. But we're going to use this for part 3, where it asks us, does this molten alloy form an ideal solution? So remember when we were talking about ideal solutions, or somebody asked me, and basically an ideal activity level is equal to the molar fraction. So the more you have, the more it's going to like act, in the activity sense. That was a terrible explanation, but it makes sense that they would relate to each other linearly if we're having an ideal case. Nice and, we're going to have that little plot. Activity, xi, 1, 1, we're going to have a straight line up there. Oh, it's not going to go. That's such a mood. Okay. There we go. It's going to look like that. So in this case, we need to figure out. Go for it. Yeah.
So I think I'm having hard. I get kind of confused with like what's the pressure and pressure saturated.
Okay.
Can you help me figure it out and explain it? Because like so the pressure that we found using that equation way back in 1, that was the saturated.
Yes.
Okay. And then we then found the partial pressure. Like how can you explain to me a great way or maybe just an average way? I'm just like putting those two things up in my head. Like
So-
know what when I find what one actually is.
Okay. So I guess just in general, let's say we have a crucible, right? And all we have in here, this is entirely Mg. All we have in here is Mg. It's gonna, and then we pass argon over top. Yay. what's going to happen is that some of this magnesium is going to go up into the gas, right? And you're going to put as much magnesium, because magnesium is like, I don't care if I'm in gas or if I'm in, liquid, like I'm going to do whatever makes me happiest. So it's going to go up into the air and it's going to do as much as it can. And that's going to be the saturated vapor pressure because all we have is magnesium. So all of it's going to be going up into the air. That's as much as you can fit. Does that make sense?
Yes.
But if we have a solution, so now we have like Mg plus Cu, right? We're passing argon over top. Oh, that was a terrible argon. Oh. Now we have the magnesium and it's like, well, some of me wants to go, but some of me like kind of likes staying in solution, right? Not all of me wants to go up as much as I can because I'm no longer like,
They don't want to leave their friend alone.
yeah.
In the crystal.
And like there's also less of it in here, right? Because we have some magnesium, we have some Cu. So like our xmg isn't going to be equal to 1. So you can't physically have as much because for the same like quantity of like, substance you have in the crucible, you actually have less magnesium, so you're going to have less going into the air. Does that make sense?
Yeah.
So when you're dealing with a calculation, here it specifically says the saturated vapor pressure is given by this equation. So if it says saturated vapor pressure, we know it's going to be the saturated vapor pressure. That's kind of easy.
Great.
When we're dealing with PV equals nRT, this is where it gets a bit trickier, and this is where you need to think, what does it mean by saturated, right? And when we're talking about saturated, we mean the maximum amount possible. And that's where it comes down to N. Do we have the full N that could be going into the gas? In this case, we were given N is given by some change in mass. We don't know. We don't think, or I guess we don't think, but like we don't know if that's actually the full amount that could be going into the words into the gas, right?
If the system was just magnesium, we could assume that it is.
Yeah.
It's just that we have a solution. Yeah. Okay.
Yeah.
And some of it will stay with the cover.
Yeah.
So then it's only partial. And then that equation that we used, like, is like a kind of different system. It's just magnesium.
Yeah.
That's what that equation is assuming.
Yeah.
That's how we're looking
Yeah.
at that saturated pressure.
Yeah.
And then when we look at it, it's partial because it's also copper.
Yes.
Okay, yeah, that's fine.
Slay.
So if it was just magnesium, then there would be no partial pressure? Or,
Well, if it was just magnesium, let's say there was just magnesium and nothing above, right? Then whatever would go into the air, that would give you the saturated pressure. We have the argon going above, so it's just magnesium and the argon. We'd still be getting a partial pressure because we have this big volume, right? A really big volume that's taken up by other gas. That's another way that we can think about it, is this volume, right? What is this volume in relating to the amount of moles we have? In this case, volume comes from another gas.
Yeah, because it's almost like there's like an external system.
Yeah.
Because the copper doesn't leave. So it doesn't have a pressure because like
Yeah.
it's in there. It's argon that has the other pressure. But
Yeah.
But then the mole fraction of argon is just still much bigger than magnesium when magnesium goes into that like overhead system.
Yeah.
Okay. Yeah, that makes sense. I'm
Okay.
good now.
Okay. Okay.
But I don't know if my fellow colleagues are good.
Your fellow colleagues. Any other questions about this? Okay, slay. So we'll get back to part 3. Where basically, remember, for an ideal case, activity is equal to the molar fraction, right? So however much you have is however much it's going to be acting. Like I've already did that really awkward explanation of it. So in this case, we found that the activity of Mg is equal to 0.0218. So now we need to find what is xmg. We remember back in oh my gosh, at the very start when I was like, I don't actually know if we're gonna need xmg, but I'm gonna calculate it anyways, just because like it like I'm given one of the molar fractions, I'm gonna find the other one. We're gonna actually use that. Fascinating. I didn't actually know if we were gonna use that. Like I wasn't even tripping you up. I just by habit will calculate that. So we know that xmg, where was I? xmg is equal to 0.78. These two are not equal. Therefore, not ideal. Another way that we could take about it Another way that we could think about it is instead of saying AI is equal to XI, is we could say that remember, like PI is equal to XI, PI not, right? We can say this is true for an ideal case. Yes. So we could say that PM is equal to, we could take 0.78 and we have that saturated pressure, right, of like 0.0175 atmosphere. It's PMG, and you would find a value of 0.0136, which is greater than the whatever we just calculated. What was that pressure? Where do we calculate it? Greater than whatever this is, this value. So this tells you the same thing, whether we say that XI, like whether we compare X and A or whether we compare like the two pressures to each other. We know that in this case, PM ideal is greater than PM non-ideal, which is equivalent to saying XM is greater than AM. And this actually shows us negative deviation. And the reason we know it's negative deviation, I mean, you could go through the math, but I like to think of it graphically. So we can deal with it in terms of, I guess I drew the activity on the X side there. We know that for a given XI value, like let's say we're at 0.5, this is going to be greater than whatever the activity is. So if the activity was equal, it would be here, but we know that XI is bigger, so activity is going to be somewhere like here instead. It's going to be like something like that. Alternatively, PI, XI, something like this. That would be the ideal case. Here we have PI not. And we know that ideal would be here, ideal, but we're actually like somewhere over here, non-ideal. So that's going to, again, demonstrate that negative deviation because it's below. Alrighty, questions, comments, concerns? Go for it. Within rounding error. Yeah, whatever that means to you. These were very, very far apart, so
Yeah.
yeah.
I think, on the little graph,
Oh,
the
okay.
equation is y is x. And so, whether it's x is 0.5, the patient's the x is 0.5. A, right, it's not as high. So
Right.
it's like 0.3. And if it's a negative deviation. That's good.
P equals nRT.
No,
Okay, are we good to move on?
that was a doozy.
Yeah.
Yeah.
The next one was actually terrifying to look at, but really isn't that bad.
Okay.
Also, I was just checking my notifications on my watch and I just got a co-op offer that I'm gonna decline, but it makes me feel good.
Yeah.
Yeah.
It's in Halifax at a pharmaceutical company.
Yeah.
So, yeah.
I got my phone. Just wrong.
Oh. You're gonna be doing research at Mac?
I don't want to be.
I'm gonna be doing research at Mac though.
Are you?
Yeah. Not in materials,
It's
but
affiliated with Grenoble.
Okay.
So I have a French shop, and then I have
that's kind of cool.
you know.
Yeah, of course.
So
Yeah.
It's with her research.
Oh, she's so slay.
She's on top of her shit. So I might actually enjoy research this summer.
Because she's doing like a direct entry PhD, yeah, isn't it? Yeah.
Because the guy that I did last summer, I didn't really love it because like I didn't do everything. And
Oh.
he was just studying the exam all summer.
Now, Rena, she's wonderful.
Yeah. So yeah.
Okay, let's do this question now, and then we can have like fun chat times. So we're given this plot. I don't know if y'all have ever seen something like this. I sure as hell never saw anything like this in my classes, and I was like, wow, I'm so overwhelmed. But it's only 5 marks. It says 10 minutes, right? We're like, it shouldn't be that bad. So let's look at it. And it says, using the plot below, showing the variation in the integral heats of mixing for non-ideal liquid AB at some temperatures, sketch the corresponding variation of the partial molar heats of mixing components A and B with composition. Be sure to include value estimates on the plot. So look at this and we're like, wow, I don't even know what that means. So let's kind of break it down. We know that this graph, this right here, is going to be showing us, we have, oh, we're in purple. Okay, this is delta H. Well, there's a few ways we can look at this. But essentially, it's like when we're dealing, for example, you might have seen something like, the delta G of mixing versus X, right? You might have seen a graph like that. And it'd be like something like, ooh, we have G of mixing, and then we have X, and it'd be like something like that. Taking into account like H's and deltas. I don't remember what the Gibbs do him is. Maybe. I don't remember what that equation is. Words have no meaning to me. I can talk about concepts, but like actual, like what they're called, could not tell you. But essentially, when we have something like this, then, if we take intercepts of the tangents, like, what we're gonna get is we get like, for this composition, we're gonna get the delta G, delta G of mixing the contribution of A, I think this would be B, and then here, this would be delta G of mixing of A, and it's just gonna be those intercepts. The way that we can, it comes down to an equation that I don't fully remember, but I wrote this down on my test when I was trying to figure out what I did for this question. So I'm going to write it down here and maybe it'll help you. But we have, like, for example, delta G of A is equal to like G plus XB dG dXA. Is this the Gibbs do him thingamajigger? Yeah. So let's say we have this. The way I like to think about this is I know that G is equal to negative XB dG dXA plus delta G A. dG dXA is equal to the slope, right? So we can say that this is equal to, this is the slope and this is the y-int. So if we're looking at this, and if we were to take, the slope at any point, that would be the tangent, whatever that y-intercept is going to be. So like on this side, for example, that would be delta G A. Does that kind of make sense? Like this is a big thing that I do, like when I did physics labs, for example, is I try and just think of everything in the terms of y is equal to mx plus b. So whether you have like a log plot or whether you have like any funky equation, I just try and figure out what is what. So in this case, we're plotting xb. So that's going to be our x. This is going to be our slope, right? And then we're going to have our y-int right there. And that's going to give you delta GA. So that's kind of how you can think of it. And we're doing the exact same concept here, just with enthalpy instead of Gibbs free energy. So I kind of like questions like this because, I mean, like, did I freak out when I saw this on the test? Yes. But realistically, it's taking concepts that you know and not just like spitting it back out again, but it's making you think and being like, how do I transfer this knowledge? So what we're going to do then is we're just going to draw a bunch of tangents, and I'm going to do a really terrible job at drawing them because I actually don't care right now to make them good. So what we're going to do is you can just go at every single point here. I recommend bringing a ruler to any sort of thermo test this semester because you're going to have a lot of graphs to draw, and just taking the tangents. Oh, this is going to be so bad. Tangents. So this would be this point right here, for example, would be at xb is equal to 0.1. And then you take another tangent. I'm not going to do all of them. Nobody needs me to do that. Like, for example, this point right here would be xb is equal to 0.4. And this value right here, so like that would maybe be like a delta G B is equal to, I don't know, like 450. Or not delta G, delta H, B is equal to like 450 or thereabouts, etc. And then you're going to do that for all of the values. And you're going to do it the same thing for like A. Like, ooh, do this here. It'll be like, delta GA is equal to like, I don't know, like 700-ish. And then like, and this is at a value of XB is equal to like 0.7, whatever. You do that for all of the different points, do a lot of lines. It's so fun. And then what I did is I made a little XB versus delta HA of mixing, and then delta HB of mixing. And this is all in values of kilojoules per mole. And I just tabulated this all. So I said like 0, 0, 1280, 0.1, 15, 180. And then you're going to keep going. These are just all the y-intercepts that I got. And then eventually I had like 1.0, 1320, 0. So I'm not going to go through all that because it's really tedious. And then I just made a little graph. So we'll do a little arrow. So essentially what we're going to see is I made, this is going to be delta H of mixing in values kilojoules per mole. And then this is going to be, what? Okay, this is XB. So like we're going to have 0, 0.2, 0.4, 0.6, 0.8, and then 1.0. Oh, 1.0. And literally all I did is I took these values and I plotted them. And this is what I did, is I did A like this, and I did this for B. And you're going to get something that looks basically, as you get, you can kind of think of it like as you add more and more B to the system, right? Mixing that B around isn't going to change the enthalpy that much, right? So it's actually going to go down. Like as we reach like 1 XB, like a fully B substituent, like a fully B solution, you're not going to have any change in enthalpy by mixing it up a little bit, right? Like by adding any more B, you're not going to get any difference. The same thing could be said for A. So here when we have 0 XB, this is fully A, so we're going to have it equal to 0. And then the plot looked something like this. Oh, I'm doing a bad job. Obviously, I had points for like every line, but I'm kind of too lazy to draw that. Like, it looks something like this. And what we can see here, we know, basically we can see here, it didn't actually ask us to talk about this, but we can see that it's not going to be a straight line, right? That's going to be a little funky. And we know that it's going to be a little funky because it says it's a non-ideal liquid, right? So we're going to have this enthalpy of mixing. Go for it. I use the same axis for both. Yeah. I use different points for each, but they're both plotted in the same like values, right? It's like the kilojoules per mole. If you want to come look at what I did, you can. Oh, good. That's so fair. So if we had an ideal case, right? The delta H of mixing is actually equal to 0 the entire time. So it looks something like this. So the fact that we're having like a funky thing, like that kind of describes why we have the funky behavior here. Does that kind of make sense?
Plotted 2 dots.
Yeah.
Got it. Thank you.
And that was the end of the test. Was our question there? Yeah, that was all I wrote. So now it's just open question and answer time. Ask away. Go for it.
So that whole fraction, it's like we used the Gibbs to him, and like, cause I mean like apply it to the enthalpy.
Yeah.
And cause all it's saying is draw a tangent line.
Yep.
Get points.
Yep.
End of day. Go home.
Yep.
Okay.
Alyssa.
I don't know if you're gonna remember how to do this, I just thought I'd ask anyway. But do you know, like, for a question, if they ask you to estimate Henry's constant, like how you would do that?
Of course, depends on what you're given. So I'm gonna make a little line
Yeah,
here.
let's say you get like a graph, I mean a table, like pressures and.
Oh, I remember those tables. Okay.
Like I just think like the kind of like constant.
So let's remind ourselves of what Henry's constant represents, right? So Henry's constant is like what, like P I is equal to like or I guess it's represented by K. Ki times Pi naught, right? And then Ki is Henry's constant. So what this means is we have pi xi, and let's say right here, this is pi naught. In an ideal case, remember we'd have our straight line. But we don't have an ideal case. We're gonna have some that looks like, right? So ki graphically, what it represents is it represents the intersection right here. And what this, so that's graphically what it represents, that intersection. But what does it mathematically represent? Is it represents the slope of the tangent at low concentrations. So what we can do is for, like in this small little area, we can say that ki is equal to slope, which is equal to the change in pressure over the change in xi. So if you're given a table and you have a bunch of like, ooh, pressures, here's, or I guess it'd be the other way around. We're given a bunch of x, we're given p, and it's like 0, 0 0.1, 0 0.2, 0 0.3, then you're given like, I don't know, 0, like 4, 6. That's not a straight line. 3, 6, then it's like 12, you know? We can look at it and just like take the lowest couple values, whatever, you know, within reason, and just be like, okay, we're gonna take these and we say delta p over delta x is equal to k, which is equal to 6 minus 3, 0 0.2 minus 0 0.1, which would give you what, like 30. So
So you can choose like the lower.
yeah, why do we use the lower values?
Oh,
Because Henry's law applies in dilute concentrations, right? Henry's law is for really dilute systems. So that's why we want a low x value. Go for it. Such a mood.
why does K have to be less than 1?
K doesn't have to be less than 1.
But like
Is that for all cases? Cases. um, yeah, if you can bring up that specific portion of the textbook, because to me, if I think of it, it's gonna have a lot of graphs. We have, because what if we had positive deviation, right? So if we have negative deviation, then yes, it's gonna be less than 1. But what if we have positive deviation, right? We're gonna have something like this. It's gonna be a big value.
that's
I need to see this textbook section. Gascal really letting me down here. Fun fact, my dad did engineering back in like the 80s and he has a copy of Gascal. Okay, where is this?
It says like
Okay,
that's the equation, and then like KB has to be less than. It says
Give me
the
a
same
sec.
thing for KA.
Yeah. Oh my God, that's a weird page flip. Okay. This only has to do with negative deviation.
Oh, really?
Because in the sentences, it's considered the case in which AB bond energies is considerably more negative than the AA or BB bond energies. Right? So this is only dealing with the one case where it's going to be negative deviation because we have really strong AB bond energy.
So like when I'm like generally writing the Henry's law, like it doesn't have to be less than 1.
Yeah. And it comes down to like basically if it's going to be negative deviation, then Ki is going to be less than 1. But if it's positive deviation, it's going to be bigger than 1.
Oh, because it's gonna go like right over.
Yeah.
Okay. Oh, okay.
Yeah.
Okay. I had this question, but I like didn't understand positive and negative deviation.
Yeah, no, that 100% makes sense. And I'm glad we were able to sort that out.
Thank you.
The textbook's sneaky like that sometimes. Oh, somebody there's a is this chat that I have the notification on? No, it's not. Okay. Okay, any other questions? I'm gonna actually ask online real quick. Online, any last questions before I kind of close off this meeting? I'm gonna take that as a no. Yeah, for sure. I was just gonna end off this meeting and then you can ask the questions, so I'm not like worried about like what my face, not that I was worried about what my face looks like. I'm gonna take Slay. Thank you for joining online. For anyone watching this recording later, best of luck. If you have any questions, feel free to message me. I would love an excuse to procrastinate on all of my studying. Okay, that is all. Have a wonderful day.